So the session on metadata and file systems ran for at least 4.5 hours, and there were 9 different presentations. I obviously am going to go through some key points very fast, and I'll also plead quite a bit of ignorance on a lot of these topics. The session was actually organized by Henry Newman from Seagate Government Solutions. He's a well-known expert in the field. And his presentation concentrated on cybersecurity and risk management and worldwide standards. And this was his first slide. And it actually covers my total experience in computing, because I started back in 1960. I'm probably the oldest person in the room, programming on an IBM 650 in machine language, and it had a drum memory, and it had 4,000 words of memory. And this is sort of a sidetrack, but it ties into what Henry was talking about in terms of the rise of the edge and distributed computing and number of endpoints. And I think both the Panasas presentation talked to that a bit, and we'll have some summary of DMF from HPE that also talks about that subject. But, you know, I continue to be amazed, even after 59 years of working with computers. This is a recent device I ran across because I'm installing solar panels on my house. And this here is a device called Sense. It's a little bit smaller than an iPhone. And you plug it into your circuit board, and those 2 white clips monitor the incoming electricity into your house, and it takes 1 million samples a second. And it uses machine learning to identify every device that consumes electricity in your house. And obviously, it's communicating over the internet to databases that Sense.com maintains, and it's communicating data to your utility company, and I believe it's exchanging information with the manufacturers of the equipment. And it's pretty impressive. If you have 2 refrigerators of the same model, it can differentiate between the 2. It says it can differentiate between identical light bulbs in different sockets. I'm not quite certain how it does that, but of course, 1 million samples a second, that's still about 300 meters. And so, but it's obviously capturing a lot of data. It's also generating a lot of metadata. And you think about all these devices that are popping up and being installed all over, doing all kinds of different things. Definitely what Henry Newman was talking about the volumes of data, and also the volume of metadata is getting quite large. Yesterday's New York Times, actually a couple of days ago, how to stop superhuman AI before it stops us. And I took a look at this and I say, I don't worry about the robots. What I worry about is we are building global information systems. We're building global information machines. And that reminds me of a movie called Forbidden Planet from 1956, where we transferred all our knowledge, or this race of people in a distant planet transferred all their knowledge to a all-powerful planetary global system. and it wound up destroying them. But I typed in FORB for Forbidden Planet on Google, and I was shocked I got as far as FORB, and it came up with Forbidden Planet. I said, it had to read my mind. But actually, it turns out there's a shop here in Edinburgh. So, you know, it wasn't quite right, but yes, it's... so evidently it got its name from that movie. But, you know, this is in that 1956 movie. It talked about this global planetary machine. And we're getting there. Okay, back to the subject. And Henry's presentation basically concentrated on the fact that you have to have global security. Your systems need to be certified. Your network has to be secure. You have to have encryption. You have to have good security algorithms. You have to have good declassification procedures. So he went through the various standards, the FIPS standards, the common criteria certifications. We've seen some of that in play recently with the battles over equipment coming from different countries where, hey, they failed to meet their certifications. They didn't have all their paperwork. And we're buying these different pieces of equipment, building systems. How do we make sure that they're not stealing data or corrupting data? So these are certainly concerns. And I'm not going to go through all the standards, but there's many there. By the way, all of the 9 presentations are up on the HPC User Forum website. So you can download the presentations in full and read through them and take a look at these references. Okay, and now I'm getting into Rupak's area of, and this is the NASA Data and Information System for Earth Science. I did this little summary of chart to give a little overview. NASA maintains a number of distributed acquisition and archiving centers. I think there's about a dozen such centers. And those centers are centers of expertise. So if they're studying the polar ice caps, the data from the satellites go to download to a DAC that concentrates on that subject area. They have the expertise in that area, and they are responsible for the data. They do the data ingest, the processing, the validation, metadata creation, archiving, preservation, and providing for user access. So they have a limited amount of computing capacity, a large amount of data storage and archiving capacity, but their main processing facility is Rupak's out at NASA Ames. So it's kind of I think it properly recognizes the importance of the research scientist in this whole process of data ingest and validation and metadata creation and archiving and preservation. So it started in the 1990s, 11,000 plus data types, 27 petabytes of data. So again, the DACs the science investigator-led processing systems. They perform forward processing of standard data products, reprocess data to incorporate algorithm improvements, so they're responsible for their data, and they're responsible for making sure it's correct and that it's has the proper metadata, and they're responsible for its redistribution. Again, this is just another view of that. Types of data: satellite on-orbit missions, airborne systems, in situ measurement missions, application support, and earth science research support. These are activities that are allocated to the DACs. As I said, here's some of the DAC functions: ingest, producing higher level products, perform processing, archive signed data sets, export metadata to a common metadata repository. We'll talk a little bit more about that. Provide user interfaces, distribute the data, and provide metrics for managing the data. There's a slide on procedures for archiving, and obviously the whole process of planning what data is going to be acquired, how it's going to be supported, how metadata is going to be created, how data is preserved. From the HPC Center point of view, we have tools to implement, but the hard work is really taking place at the DACs, and understanding the data, understanding the needs of the research scientists, and creating data descriptions and distributing and preserving the data. So these show the core services of the DACs. It's providing maintaining the earth science holdings, providing the metadata catalog, and providing tools to allow users from around the world to access the data as appropriate. This was a schematic of the common metadata repository, and I think here is a slide that has identifies the open system tools that are used in creating the CMR and making the data available. And you can link to all of them on the web. Okay, so this is Amanda Tuminello from U.S. Navy HPC Center down in Mississippi, gave a presentation. And the Department of Defense operates 5 distributed computing centers, each one of them housing high-performance computing equipment for basically open research. And here, for political reasons, user may actually get an allocation on more than one system. And user may copy files from one center to another. So that raises some interesting questions. Well, how do you find all the copies of your data? How much data are you using? What are the I/O characteristics of the physical residence? Because each of those 5 centers has different equipment and different storage systems, and so things get a little complicated for the users because their data could be anywhere. But this is sort of, you can say, the issue of the cloud can get kind of cloudy. From a systems administration point of view, you want to know the I/O characteristics of the system and the encryption capabilities. Can you query the sensitivity levels of the data? And what's the chain of custody over the data? Who controls the data? Who does it belong to? I worked in universities for a while, and I think on many projects at a university level, it gets very confusing because the researchers come and go fairly frequently. They're graduate students, they graduate, they move on. How do you maintain project control over all the data aspects? And it's not so different in the Department of Defense open research computing centers. Again, if you're planning, this is from a systems point of view, if you're planning new acquisitions, what data do you need to figure out what new systems should you acquire? I think in the case, for example, of the European Center for Medium Range Forecasting, it's a single focus research facility. Here, it gets a little bit confusing because there's all kinds of research activities going on. It isn't a single mission. It's multiple missions. Tara Russell from the RENC, from IRODS, that's the Independent Rule-Oriented Data System, from Renaissance Computing Institute, University of North Carolina, spoke. This is a open source archiving metadata system. You can join the consortium and they will provide some support, but basically it's an open source product. It's been around a long time. It is metadata driven and it's constantly enhanced, and it addresses the issues of creating metadata from edge devices and as well as user-driven metadata development. So his presentation is pretty complicated. It's a pretty complicated system, but it does support automated ingest, auditing, indexing, data integrity, storage tiering, provenance, publishing, and compliance. And it says basically as you go from small research projects to more formal, larger projects, the process gets more involved. And again, the issue of developing metadata standards is very, very critical and something you have to work closely with the research community to do. One of the nice things about IRODS, it's independent of file systems and the HPC hardware. So you can have, let's say with the DoD, you can have 5 separate centers. They can have different mainframe HPC systems. They can have different file system software, but IRODS will work with any one of those. So one center will have an IRODS implementation. You can have with Panasys, and another center could have IRODS with GPFS, for example. You can federate those IRODS servers, and so you can search across the metadata of multiple centers using different file systems. And it implements security at a systems administrator level, and as the data owner can also establish their own security protocols. I am not going to go through these slides. They're available on the web. They're kind of detailed and kind of hard to read. But it does provide, unified namespace, long-term storage, federation with other organizations. Okay, so the takeaways about iRODS: one, it's open source. You can get support. There's, I believe, also these days a commercial company that provides iROD support. It's automatic policy-based solutions. It has a programmatic interface to the rule engine via policy enforcement points, and can support all those functions that are necessary for creating metadata and providing access and archiving data and auditing and reporting. Let's see, this was a presentation by Kirill Malkin from now with HPE, and so this here is DMF is a product that originated at Cray, and then it went to SGI, and it's now with HPE, and it's being, when it was with SGI in the end, it sort of support waned on it, but HPE is making a major effort to reinvigorate it, and obviously it be available on HPE as well as former SGI and Cray products. And again, and this is somewhat like the Panasys discussion of yesterday, and it discusses the issue of edge computing and IoT devices and moving both the data closer to the IoT devices because data transfer is taking too long. And AI, big data, and HPC processing gravitates to many data centers at the edge. But the still, you need to aggregate and preserve the data and be able to access it. And it provides the metadata tools to do that. It is not 100% POSIX compliance, but it's moving towards better POSIX compliance. So again, the objectives is to maintain namespace reflection with file and directory metadata that can be queried independently of the file system or data. And that's similar to iRODS and Panasys. An important thing is transparently migrate and recall files on different systems, Lustre, HPC, HPE, XFS, and other parallel file systems. So, it's based upon a scalable metadata repository. They give some examples of the type of metadata that you can add, and the queries can be against the metadata extended attributes. So again, like some of the other systems that we've seen, is it's independent of the type of file systems that are used in the storage devices. The iRODS and Panasys and DMF work across tape storage, NVMe, and on-premise object storage or off-site cloud storage. So in summary, it provides for tiered storage, metadata search, and right-size flash-based burst buffer namespaces. And we're seeing that across various products. And that, I think, ends my presentation. But again, all those 9 presentations are on the web, on our website, and you can download them. Okay?
Well, thanks.
Thank you.